Let's think about this. The situation with the lift was rather simple when we could call lift is rho half v square CLS. Drag is a bit more complicated because we say our total drag is our parasite drag plus induced drag, or this is form drag plus skin friction drag plus interference drag and other components plus the induced drag. Now some ask me, which one do I have to use when? So let's have a closer look into this. Any object traveling through a fluid experiences parasite drag. That's the reason why we single out parasite drag. Parasite drag is proportional to the square of speed. This is the big element. Also, the parasite drag is proportional to the frontal area. It is proportional to the surface area, and it is a function of the form of the object. So let's start with the last one. Let's look into the form of the object. Now this is an example from the 1920s, 1930s of the last century, or 90 plus years ago. The left steam locomotive and the right steam locomotive are the same model, only the right locomotive is covered by a streamlined skin. Now you would think this extra weight doesn't pay off, but these locomotives were going 130 to 150 kilometers per hour, and above about 80 kilometers per hour this additional skin would pay off big time. So what we can say here is that our form drag is influenced by the form of the object, and we cover this form drag in the C drag form, and the one on the left hand side is much bigger than the one on the right hand side. If you continue and look into this object here, then we can see another of those streamlined locomotives. The Germans were very famous for those. And what you see is that it's not only the frontal part of the locomotive which is streamlined, and not only the sides, but it is the rear part of the whole train. In fact, that was the famous Henschel-Wegmann-Zug, which drove 160 kilometers per hour, and the whole train was designed in the wind tunnel altogether from front to tail. And we can look at the consequences out of this. Another German-made train, contemporary nowadays in use in Germany, and doesn't it look like the Henschel-Wegmann-Zug? If we look into positive use of form drag, then we have here the drag chute of an F-16, which helps to slow down the aircraft after landing. So all we do here is we increase the frontal area, having a rather unfavorable form of the object. So actually we want to have a high CD form. We want to have a high form drag in order to reduce the speed. The big disadvantage here is that the form drag is proportional to the power of 2 of the speed. So once the aircraft actually slows down, the effectiveness of the drag chute reduces dramatically by the power of 2. Let's look at this one. That's a totally different story. Here we have a huge surface of the vessel. So look into the left picture, that's New York underneath, and the right picture, I inserted this one to show you the size of this airship. You see the small people and this huge size of this airship. In fact, it is, I'll give you a few numbers here, length is 260 meters, the diameter is above 42 meters, and the surface area of the skin is about 34,000 square meters. 34,000 square meters. Now, here it becomes obvious that you face a problem with skin friction drag. So let's have a quick look into this situation. So you remember, skin friction drag is rho half V square. This is our dynamic pressure times a CDFR times the wetted surface. Now here's my big problem. The surface, the huge surface of this vessel makes it a problem. Let's look into real numbers. So we can say our skin friction drag is rho half 1.225 kilogram over cubic meter divided by 2 times the speed of this vessel was 125 kilometers per hour. That makes it roughly 35 meters per second. 35 square meters square over second square. The coefficient of skin friction was about 0.015. It's a small number. No dimension because it's just a coefficient. Times, and now is the big multiplier, 34,000 square meters. Now the result of this one is roughly 382,660 Newton, or roughly 383 kilonewton. That's an incredible big number, and that in fact limited the speed of that craft to 125 kilometers per hour. If they would have driven faster, they would have run out of fuel relatively quick because of the dependency of the drag and the speed. So two problems: huge surface and speed limited. To summarize at this point, any vessel within a fluid in motion experiences parasite drag. Parasite drag is certainly form drag, depending on speed, form and frontal area. Skin friction drag, depending on the quality of the surface and the size of the surface, and again the speed. And we have another form of drag, which is interference drag, in which we didn't look so much at the moment, but we will have a look at another time. Now, once you look into lifting, aerodynamic lift, the moment you produce aerodynamic lift, you have the problem of lift-induced drag. Again, the lift-induced drag is proportional to the power of 2 of speed. It is proportional to the surface area of the lift-producing surface, and there is a coefficient. Now, I found this in the NASA website. They actually can relate the drag coefficient for the induced drag, CDI, to the aspect ratio. You remember whether this is a slender wing or is a more stubby wing. Now here you can see, since the aspect ratio is in the denominator of the fraction, a good, meaning large aspect ratio, a slender wing, reduces the induced drag. And we remember that the induced drag is, as usual, rho half V square, our dynamic pressure, times that factor, CDI, times the surface of the object. Now, when do you have to use which drag form? Now, anytime you move in a fluid, you have parasite drag. That means my total drag always has the parasite drag component. Anytime you produce aerodynamic lift, you add your induced drag to it. And we will get to know other drag forms, for instance wave drag if you fly very fast. And that's the way it is.